Fine. Let's start. Number 16. WOH G64. Picture a star so large that if you dropped it where our sun is, its surface would swallow Mercury, Venus, Earth, Mars, and keep going, out past the asteroid belt, reaching for Jupiter. That's WOH G64. It's a red supergiant sitting about 160,000 light-years away, not even in our galaxy, but in the Large Magellanic Cloud, a little satellite galaxy that orbits the Milky Way, and it is roughly 2,000 times wider than the Sun. Astronomers just call it the Behemoth. For most of the history of astronomy, there was a hard rule. We could see the surfaces of exactly one star in any detail, and that star was the Sun. Every other star, no matter how big, was a single point of light. Too far, too small on the sky. Just a dot. Then, in 2024, that rule broke. Using the Very Large Telescope in Chile, a team took the first close-up image of a star outside our own galaxy. Not a dot, an actual picture, showing structure, showing shape. The first time we've ever resolved the face of a star belonging to another galaxy. And here's the thing. What they found wasn't a clean, round ball. It was a star wrapped in an egg-shaped cocoon of its own gas and dust, material it has been coughing off its outer layers over the last few thousand years. The cocoon was stretched, elongated, far more lopsided than anyone's models had predicted. Nobody fully knows why it's that shape. Then came the second wave. Because a red supergiant puffing out its guts like that is doing something specific. It's dying. WOH G64 is in the last act of its life, the stage right before a star like this detonates as a supernova. We are looking at a giant in the process of coming apart. And the strangest part is the timing. We caught it now. Out of the entire lifespan of a star, millions of years, we happened to point our best telescope at it during the brief, final chapter, and watched it building the shroud it will die inside. 2,000 suns wide, 160,000 light-years away. And for the first time, close enough to see its face. And for one quiet moment, in a galaxy that isn't even ours, a dying giant let us look it in the eye. Number 15, Milky Way, the garnet star. Go outside on a clear night. Look toward the constellation Cepheus, and with a little patience, you can find a faint, deep red dot. That dot has a name that goes back more than 2 centuries. William Herschel, the man who discovered Uranus, looked at it and called it the garnet star because of its extraordinary color, a red so rich it looks like a gemstone. What you're seeing with your own eyes is a red supergiant somewhere around 1,000 to 1,650 times the width of the sun. Let that sink in. This isn't a photograph. This isn't data on a screen. This is a star you can personally see, standing in your backyard, that is so enormous that if you placed it where our sun sits, its surface would reach out past Earth, past Mars, past Jupiter, all the way to the orbit of Saturn. Everything we think of as the inner solar system, the warm, familiar part, would simply be inside this star. The color isn't just pretty. It's a symptom. Milky Way glows red because it's relatively cool for a star. Its surface swollen and stretched thin as it burns through the last of its fuel. Big, cool, and red is what a massive star looks like near the end. The garnet glow is the color of age, and it's restless. Milky Way is a variable star. It doesn't shine steadily. It pulses, brightening and dimming over months and years as its bloated outer layers heave in and out, like a chest breathing. It's shedding material too, building up clouds of dust around itself. The early stages of the same process we saw tearing at WOH G64. Here's the part that gets me. It sits about 2,800 light-years away, which is far, genuinely far, and yet it's still bright enough to catch with the naked eye. For something that distant to be visible at all, it has to be pouring out a staggering amount of light. You're not seeing it because it's close. You're seeing it because it's monstrous. So the next time someone tells you the night sky is just tiny pinpricks, find that red dot in Cepheus. Because one of those pinpricks is a dying giant, wide enough to bury Saturn's orbit inside it. It's been hanging there in our sky the whole time. We just call it a star. Number 14, NML Cygni. Now we go to a star that's trying to hide. NML Cygni is a red hypergiant in the constellation Cygnus, and it belongs to the same club as the giants we've been talking about, except it may be even bigger. Estimates for its radius run from around 1,100 solar radii to as high as 2,700. At the upper end, that's a star so wide that it would engulf the orbits of the inner planets and reach well beyond, deep into the outer solar system. But size isn't the strange part. The strange part is what it's doing to itself. NML Cygni is wrapped in a thick cloud of gas and dust, and it made that cloud itself. As a hypergiant, it's constantly blowing its own outer material out into space, and around this particular star, that material has piled up into a dense, dusty shell. So much of it that the star is being dimmed by its own exhaust. It's smothering in a fog of its own making. Think about what that means. Here is one of the largest and most luminous stars in the entire Milky Way, pumping out something like 229,000 times the light of the sun. It should be blinding. And instead, it's veiled, muffled, partly hidden behind the dust it keeps spitting out. A giant disappearing behind a curtain, it's weaving in real time. For a long time, this made NML Cygni genuinely hard to pin down. You can't easily measure something you can barely see through. It took precise radio astronomy, tracking the star's position with continent-spanning arrays, to finally nail down its distance, somewhere around 5,300 light-years, and confirm just how extreme it really is. And the dust keeps coming. More recent observations traced shells of it stretching out to around 2,000 times the Earth-Sun distance from the star, an asymmetric, lopsided halo of debris. This thing isn't just big. It's actively unmaking itself, shedding mass at a furious rate, thinning out into the space around it. That's the fate waiting for the biggest stars. They don't fade quietly. They swell, they redden, and they start throwing their own bodies into the dark, until one day, there's not enough left holding together, and the core gives out. NML Cygni is that process, caught in the middle. A star so large, we struggle to measure it, slowly vanishing inside the shroud it can't stop making. Number 13. Westerlund 1. So far we've been talking about single stars. Now let's talk about what happens when you take tens of thousands of them and pack them into one place. Westerlund 1 is the most massive young star cluster known in the entire Milky Way. When astronomers add up everything inside it, they land on a mass somewhere between 50,000 and 100,000 times the mass of the Sun, all of it in the form of stars, and all of it crammed into a knot of space that, on a cosmic scale, is tiny. And these aren't ordinary stars. Westerlund 1 is a nursery of giants. It's stuffed with the most extreme stellar heavyweights we know of: red supergiants, blue supergiants, rare Wolf-Rayet stars that burn so hot and hard they strip themselves bare. Some of the largest individual stars in the galaxy live inside this one cluster, shoulder to shoulder. Now, here's what makes it so unsettling. All of these stars are young, less than 10 million years old, which for a star is barely out of the womb. They form together from the same collapsing cloud in a single burst of creation. And massive stars live fast and die young. So Westerlund 1 is a countdown. Every one of those monster stars is racing toward the same ending, a supernova. And because they're all roughly the same age and all enormous, they're going to start going off in a cascade. Over the next few million years, this beautiful dense cluster is going to detonate. One titanic explosion after another, until it has salted the surrounding space with the wreckage of hundreds of dead giants. It's a swarm of stars building its own graveyard. We already have a preview. Buried inside Westerlund. One is a magnetar, the ultra-dense, ferociously magnetic corpse left behind when one of the cluster's stars already died. That single dead star had to have been a true behemoth in life, and it's a sign of what's coming for all the others. There's really only one other kind of object in the galaxy that reaches this kind of mass, the ancient globular clusters, tight balls of hundreds of thousands of stars. But those are old, some of them nearly as old as the universe itself. Westerlund 1 is the opposite. It's got the mass of a globular cluster, but it's brand new, still glowing, still complete, still holding all its doomed giants in one place. For now, number 12, Sagittarius B2. Let's leave the stars for a moment and talk about the stuff stars are made from, because near the center of our galaxy, there's a cloud so large it deserves its own place on this list. Sagittarius B2 is one of the most massive molecular clouds in the entire Milky Way. We're talking about a reservoir of gas holding roughly 10 million times the mass of the Sun, sprawled across about 150 light-years of space, sitting near the crowded, chaotic galactic center about 26,000 light-years from us. That's the scale. Millions of suns worth of raw material, drifting in a single dark cloud. But that's not why Sagittarius B2 is famous. It's famous because of what's in it. When astronomers pointed their instruments at this cloud and read the chemical fingerprints in its light, they found it packed with complex molecules, more of them than almost anywhere else in the galaxy. Ethanol, which is drinking alcohol. Methanol. Propanol. And, memorably, a compound called ethyl formate. Ethyl formate happens to be one of the molecules that gives raspberries their flavor. It's also a big part of why rum smells the way it does. So somewhere out there, near the heart of the Milky Way, floats a cloud the mass of 10 million suns that, chemically speaking, is laced with the taste of raspberries and the smell of rum. The galactic center is, in a very loose sense, a distillery. Now, I want to be careful here, because the fun version of this story gets overblown. You could not fly out there and drink it. The cloud is almost unimaginably thin, a near vacuum by our standards, and it's swimming in plenty of molecules that would kill you long before any of it got you tipsy. The raspberry rum thing is a real detection, but it's a garnish, not a cocktail. The deeper point is the one that actually matters. Sagittarius B2 shows us that the complex, carbon-rich chemistry that life is built from doesn't need a planet to get started. It can assemble itself in the cold and the dark, floating in a giant cloud between the stars, before a single world has even formed. 10 million solar masses of gas, quietly cooking up the ingredients of sweetness and life in the middle of the galaxy. The universe was doing organic chemistry long before we showed up to taste it. Number 11. UGC 2885, Rubin's Galaxy. Now we step up again, from clouds inside our galaxy to entire other galaxies, and we start with one that makes the Milky Way look small. Our galaxy is not tiny. It's a big, respectable spiral, about 100,000 light-years across, holding a few hundred billion stars. For most of cosmic history, that would be a perfectly impressive thing to be. And then, there's UGC 2885. This is a giant barred spiral galaxy sitting in the constellation Perseus, and it is one of the largest spiral galaxies we've ever found. Depending on how you measure it, its disk stretches somewhere between 400,000 and over 800,000 light-years across, several times the width of the Milky Way. It holds on the order of 10 times as many stars as our galaxy does. Roughly 1 trillion suns, wound into one enormous pinwheel. It's got a nickname. Astronomers call it Rubin's Galaxy, in honor of Vera Rubin, the astronomer whose work on how galaxies rotate gave us some of the first hard evidence that dark matter is real. This galaxy was one of the objects she studied, and slapping her name on a giant felt right. One researcher described it in a way that stuck with me. They said it's about as big as you can make a disk galaxy without hitting something else. It's near the physical limit. Grow much larger, and it would start running into neighbors, colliding, merging, losing its shape. UGC 2885 sits right at the edge of how large a calm, orderly spiral is allowed to get. And calm is the key word. You might expect a galaxy this enormous to be a violent place, blazing with new stars, tearing itself up. It isn't. Rubin's Galaxy is serene. It's a gentle giant, quietly turning, forming stars at a leisurely pace, showing no signs of the chaos you'd think its size would demand. It just grew, slowly and peacefully, into a monster. Imagine the view from a planet somewhere inside it. The night sky would be drowning in stars. The galaxy stretching overhead would be so vast that the light from its far side, left on a journey nearly 1 million years long, just across to the other edge. Our whole galaxy, the entire Milky Way, everything we've ever mapped, would be a suburb next to this thing. A single, quiet spiral, sitting near the maximum size the universe allows, turning in the dark like it has all the time in the world. Number 10. Malin 1. Here's a question that sounds like a riddle. How do you lose a galaxy that's 6 times bigger than the Milky Way? The answer is Malin 1. And the answer is that you make it out of light so faint you can look right at it and see nothing. Malin 1 is a giant low-surface brightness galaxy, and those words are doing a lot of work. Its disk spans something like 650,000 light-years. Maybe more. Some estimates push it towards 750,000. That's 6 or 7 times the diameter of our galaxy. By raw size, it's one of the largest spiral galaxies ever discovered. But its stars are spread so thin, scattered across such an immense area, that the whole thing barely glows. Where a normal galaxy concentrates its light into a bright, obvious disk, Malin 1 takes roughly the same amount of shining material and smears it across a colossal volume. The result is a galaxy that's enormous and almost invisible at the same time. That's why nobody noticed it for so long. It was discovered in 1986 by an astronomer named David Malin, and even then it was almost an accident. This giant had been sitting there in the sky, spanning an area larger than most galaxies we'd ever cataloged, and it had gone completely unseen because it simply doesn't shine brightly enough to jump out. A colossus, hiding in plain sight, behind nothing but its own faintness. Think about what that implies. If a galaxy this big could stay hidden until the 1980s, purely because its light is diffuse, then how many more of these ghost giants are out there? How much of the universe is made of enormous, faint structures we've been staring straight through the entire time? Because our telescopes are tuned to look for bright things. Malin 1 is a warning about our own instincts. We map the cosmos by chasing light, the bright galaxies, the glowing cores, the obvious targets. And here's a galaxy that's among the largest we know of, that broke that method just by being dim. It's still there right now, turning slowly, 6 or 7 Milky Ways wide, so faint that even knowing exactly where to point, it's a struggle to see. A giant made of whispers. The universe doesn't owe us the courtesy of being visible. Number 9. A2261 BCG. This one is a galaxy with a hole in the story. A very specific, very large hole. A2261 BCG is the brightest, most massive galaxy at the center of a cluster called Abell 2261, sitting about 2.7 billion light-years away. It is a genuine monster, an elliptical galaxy roughly 1 million light-years across, up to 10 times the size of the Milky Way. A giant among giants. But that's not what makes it strange. What makes it strange is its heart. At the center of A2261 BCG is the largest galactic core ever observed, a puffed-up, diffuse central region about 10,000 light-years across. And in that enormous core, there should be something. Every big galaxy we know of has a supermassive black hole anchored at its center, and based on this galaxy's sheer size, the black hole hiding inside it should be a titan, somewhere between 3 billion and 10 billion times the mass of the Sun. Astronomers went looking for it. They pointed the Chandra X-ray Observatory at it. They used the Hubble Space Telescope. They brought in the Very Large Array, every tool we have for detecting the telltale signs of a supermassive black hole. And they found nothing. No X-ray glow, no compact source, no signature. The black hole that should sit at the center of this galaxy is, as far as we can tell, missing. So where did a 10 billion solar mass black hole go? The leading explanation is almost hard to believe. When two galaxies merge, their two central black holes spiral together and eventually combine. And under the right conditions, that violent merger can give the newly formed black hole a kick, a recoil, launching it out of the galaxy's center at tremendous speed. The huge, sloshed-out, oversized core of A2261 BCG looks exactly like the wreckage such an event would leave behind. Which means, somewhere out there, there may be a black hole with the mass of billions of suns, torn loose from its home, drifting through intergalactic space with no galaxy around it. A rogue giant, evicted from its own heart. Now, it's not fully settled. Maybe the black hole is just dormant and quiet, hidden somewhere in that vast core, not giving off any signal. Maybe it's offset, but still bound. We genuinely don't know. But either answer is unnerving. Either there's a runaway monster loose in the dark, or there's a black hole big enough to power a quasar sitting in total silence, so still we can't even find it. Number 8. The M87 black hole. For all of human history, black holes were an idea, a prediction, math on a page. Something we were confident existed, but had never, ever actually seen. You cannot photograph a thing that swallows light. It seemed like a permanent limit. Then, on the 10th of April, 2019, that limit fell. Humanity looked at a photograph of a black hole for the first time. The black hole lies at the center of a galaxy called M87, about 55 million light-years away, and it is not a modest one. It weighs in at around 6.5 billion times the mass of the Sun. Its event horizon, the point of no return, is larger than our entire solar system. You could drop the Sun, all the planets, and the whole span of Neptune's orbit into it, and have room to spare. To photograph it, astronomers did something almost absurd. A single telescope big enough to see it would have to be the size of the Earth. So they built one. They linked radio telescopes scattered all across the planet, from Hawaii to Spain to the South Pole, and combined their data so that together they acted like one Earth-sized eye. Only then was the resolution sharp enough to catch it. And what came back was that now famous image, a glowing orange ring of light wrapped around a circle of perfect darkness, the shadow of the black hole itself. Here's the detail that breaks my brain. That bright ring isn't the black hole, and it isn't even a simple halo of gas. Some of the light in that ring came from behind the black hole, from material on the far side, and the black hole's gravity is so intense that it bent that light, curved it right around the back, and threw it toward us. You are, in part, looking at the far side of the black hole, wrapped around the front. Gravity is acting as a lens on reality itself. They gave it a name, Pauehai, drawn from an ancient Hawaiian creation chant. It means, roughly, the embellished dark source of unending creation, which is about as good a description of a supermassive black hole as anyone's ever managed. 6.5 billion suns, crushed into a single point, so heavy that light itself has to obey it, bending around its shadow to show us its face. We spent a century sure these things were out there, and then, one day, we finally saw one look back. Number 7. The NGC 4E889 black hole. The M87 black hole was loud. It has a jet. It has a glow. It announced itself. This next one is the opposite. This one is silent, and the silence is the scary part. NGC 4E889 is a large elliptical galaxy sitting in the Coma cluster, about 300 million light-years away. From the outside, it looks calm, unremarkable, a smooth blob of old stars. But at its center sits one of the most massive black holes ever directly measured, weighing in at roughly 21 billion times the mass of the Sun. Let me try to make that number physical. The event horizon of this black hole is about 130 billion kilometers across. That's roughly 15 times the width of Neptune's entire orbit. You could line up our whole solar system, edge to edge, more than a dozen times across the mouth of this thing before you spanned it. To weigh it, astronomers used the Gemini North Telescope to measure how fast the stars near the galaxy's center were whipping around. 63 separate measurements, fed into models running on a supercomputer, all to answer one question: how much mass has to be hiding in there to fling those stars around that fast? The answer came back in the billions upon billions. And here's what makes it eerie. It's quiet. It's dormant. This black hole isn't actively feeding, isn't blazing as a quasar, isn't doing much of anything we can see. It just sits there. But it wasn't always this calm. To grow to 21 billion solar masses, a black hole has to eat, ferociously, for a very long time. In its youth, this thing would have been one of the brightest objects in the universe. A quasar pouring out the light of trillions of suns as it devoured everything within reach. Now the plates are clean. It has consumed the gas, the dust, the stars that once fed it, and with nothing left nearby to swallow, it has gone quiet. Not because it's weak, because it's finished. It ate its fill and went still. Compare it to the black hole at the center of our own galaxy, Sagittarius A star, which is a mere 4 million solar masses. NGC 4889's black hole is thousands of times heavier. Ours is a house cat. This is the thing in the dark that the house cat is afraid of. A monster 15. Neptune orbits wide, sated, patient, silent, sitting in a galaxy that, from the outside, looks like nothing at all. Number 6. RX J1347. Up to now, we've been climbing a ladder. Single stars, then clusters, then galaxies, then the black holes at their hearts. Now, we take the biggest step yet to an entire cluster of galaxies bound together into one object, and one of the most extreme examples known. RX J1347 is the most X-ray luminous galaxy cluster we've ever found. It sits billions of light years away, and it contains something on the order of 2,000 trillion times the mass of the Sun. 2 quadrillion solar masses held together in a single gravitational system. But here's the twist that always gets people. If you took a normal photograph of this cluster, you'd see galaxies. Hundreds of them, glowing points and smudges of starlight. And you would be looking at only a sliver of what's actually there. The galaxies are the least of it. Most of the ordinary matter in a cluster like this isn't in the galaxies at all. It's in the space between them, in the form of gas. And this gas is not gentle. It has been heated, by the sheer gravity of the cluster, to temperatures over 100 million degrees. So hot that it doesn't glow in visible light at all. It glows in X-rays, blazing across the cluster in wavelengths our eyes can't see. RX J1347 shines in X-rays more brightly than any cluster known. It's a furnace filled with gas hotter than the core of the sun, spread across millions of light years. And in one region where astronomers think a collision is happening, a second cluster smashing into the first, the gas may be shock heated to a few 100 million degrees, an almost incomprehensible temperature for something spread that thin. And even all of that superheated gas, all those hundreds of galaxies, is still only a fraction of the cluster's mass. The overwhelming majority is dark matter, invisible, undetectable, except by its gravity, the scaffolding that holds the whole burning structure together. So picture it. Hundreds of galaxies, each with hundreds of billions of stars. An ocean of gas between them hotter than the inside of a star, glowing in a light we can't perceive. And beneath it all, a vast invisible web of dark matter, 5 or 6 times heavier than everything else combined, doing the actual work of holding it in one place. 2 quadrillion suns, a city of galaxies, burning in the dark, mostly made of things we cannot see. Number 5. Able 1689. Now, we get to a cluster so massive that it does something to space-time you can actually watch. Able 1689 is one of the most massive galaxy clusters known, and when the Hubble Space Telescope turned to look at it, it captured one of the most beautiful and unsettling images in all of astronomy. Around the dense golden core of the cluster, space is threaded with dozens of thin blue arcs, curved streaks of light bending around the cluster like ripples around a stone. Those arcs are the whole story, because they're not part of the cluster at all. Einstein told us that mass bends space, and that light has to follow the curve. Pile up enough mass in one place, and it will warp the space around it so severely that light passing by gets bent, focused, distorted, exactly like a lens. Able 1689 has so much mass concentrated at its center that it acts as a giant gravitational lens. The blue arcs are galaxies. Galaxies sitting far, far behind the cluster, billions of light years further out, whose light was on its way past when it fell into the cluster's gravity and got bent toward us. Their images have been stretched into arcs, smeared, and in many cases multiplied, so that the same background galaxy appears several times in different spots. Astronomers have found dozens of these multiply-imaged systems in this one cluster, more than almost anywhere else in the sky. And now the part that should genuinely disturb you. Astronomers can measure exactly how much mass it takes to bend the light that severely. Then they add up all the visible matter, every galaxy, all the glowing gas. And that visible matter accounts for only about 1% of the mass needed to explain the bending. 1%. The other 99% is unseen. Most of it is dark matter, the invisible substance that outweighs everything we can see many times over. Able 1689 is, in effect, a demonstration you can look at. The arcs are drawn by mass, and the mass drawing them is almost entirely invisible. You're seeing the shape of the dark matter, sketched out in bent starlight, even though you can't see the dark matter itself. A cluster so heavy it turns space into a lens. And the thing doing most of the bending is something we've never directly seen and still don't fully understand. We just get to watch its handwriting, written in the arcs of distant galaxies. Number 4. The Boss Great Wall. We've gone from stars to clusters. Now we go one level higher, to the largest structures the universe assembles, where clusters themselves become the building blocks. Galaxies gather into clusters. Clusters gather into superclusters. And superclusters, it turns out, can gather into something even bigger. Walls and threads of matter that stretch across distances the mind simply cannot hold. In 2016, astronomers mapping the sky with a survey called BOSS, the Baryon Oscillation Spectroscopic Survey, identified one of these. They called it the BOSS Great Wall. It's a connected complex of superclusters, two enormous walls of galaxies, plus two more massive superclusters, all linked together into a single structure spanning around 1 billion light years. 1 billion light years. Let me try to make that mean something, even though it can't fully. Light from the far side of this structure, traveling at the fastest speed the universe permits, would take 1 billion years to reach the near side. The wall is so large that it holds roughly 800 galaxies, bright enough to count in the survey, and its total mass runs to something like 100,000 trillion times the mass of the Sun. It's about 2/3 larger than the previous record holder, the Sloan Great Wall. And here's why a structure like this is more than just a big number. It pokes at one of the central assumptions of cosmology. We have this principle, the idea that if you zoom out far enough, the universe should look smooth and even, the same in every direction, no giant lumps. It's the assumption a huge amount of our understanding is built on. Structures like the BOSS Great Wall are lumps, very big lumps, big enough that some astronomers look at them and ask an uncomfortable question. Did the universe really have enough time, since the Big Bang, to pull matter together into something this enormous? Gravity works slowly across these distances. Assembling 1 billion light-year wall is a tall order for a universe that's only around 14 billion years old. There's active debate about it. Some argue these walls are real, bound structures that challenge our models. Others argue they're more like chance patterns in the cosmic web, and that if you average over a big enough volume, the smoothness holds up. But standing here, looking up at it, the debate almost doesn't matter. 1 billion light-year wall of superclusters, glittering with galaxies, sitting out there in the deep universe. Whatever it means, it exists, and it barely fits inside a human thought. Number 3, the Pisces-Cetus supercluster complex. Everything we've looked at so far has been out there, distant, something you point a telescope at. This next one is different, because this one is where you live. Back in 1987, an astronomer named Brent Tully was mapping how galaxies are arranged in our corner of the universe, and he traced out an enormous structure, a galaxy filament stretching about 1 billion light-years long and 150 million light-years wide. He called it the Pisces-Cetus supercluster complex. Now follow the chain of addresses, because this is where it gets personal. Our planet orbits the Sun. The Sun is one of a few hundred billion stars in the Milky Way. The Milky Way is part of a small collection of galaxies called the Local Group. The Local Group sits in the outskirts of the Virgo supercluster. The Virgo supercluster is one lobe of a much larger structure called Laniakea, and Laniakea is part of, connected into, the Pisces-Cetus supercluster complex, which means this billion light-year filament isn't something out there at all. It's your home address, the biggest line of it. You are inside one of the largest known structures in the universe, right now, as you listen to this, and you can't feel a thing. That's the part that gets me. This structure is so vast that the light needed to cross it takes 1 billion years, and you are embedded in it, riding along inside it, and there is absolutely no sensation of it. No horizon, no edge, no hum. It's roughly 10,000 times the size of the Milky Way, and from the inside, it's completely invisible, because it's simply too big to perceive. We only know it's there because we mapped thousands of galaxies and stepped back far enough to see the pattern they make. Think about how strange that is. You will never see the thing you're inside of. No human ever will, not directly. We are like a single bacterium living on one grain of sand, trying to comprehend the whole beach, except the beach is 1 billion light years long, and we figured out its shape anyway, from the inside, using math and patience. There's a humility in that, and also something oddly comforting. We are unbelievably small. 1 billion light-year structure holds us the way an ocean holds a single drop, but we're the drop that learned the shape of the ocean. Number 2. Holmberg 15A. We've saved the heaviest single object for nearly last, and this one is heavy in a way that redefines the word. At the center of a galaxy cluster called Abell 85, about 700 million light-years away, sits a supergiant elliptical galaxy called Holm 15A. And at the center of that galaxy is a black hole that, when astronomers finally weighed it directly in 2019, came back at roughly 40 billion times the mass of the Sun. 40 billion. This is the most massive black hole ever measured by directly tracking the motion of the stars around it, the gold standard method. Watching how matter moves and calculating what has to be there to move it that way. Not an estimate from brightness, a direct weighing. And the scale of it strains language. Its event horizon is so large that it would swallow our entire solar system, not just once, but many times over. Everything, the sun, all the planets, the Kuiper Belt, the whole span of everything we call home, would vanish inside it and leave the horizon looking barely disturbed. This is a single object, one point in space, that outweighs entire galaxies worth of stars. And here's how it got that big, and it's grim. When astronomers looked closely at the galaxy Holm 15A, they found its center was strange, scoured, dim. The core was missing the dense crowd of stars you'd normally expect at the heart of a giant elliptical, spread out and depleted across an enormous region. It's as if something had cleared the neighborhood. Something did. As this black hole grew, likely through the merging of smaller black holes when galaxies collided, it flung the surrounding stars away, slingshotting them out of the core, hollowing out the center of its own galaxy. The absence of stars is the fingerprint of the monster. You can read its history in the emptiness it left behind. Now, you may have heard of TON 618, a distant quasar with a black hole sometimes quoted at 66 billion solar masses, even bigger than this. And it might be. But that number comes from indirect estimates, reading the light of the raging gas around it. Holmberg 15A holds a different, colder title. It's the most massive black hole we have ever directly, dynamically weighed. We didn't infer it. We measured it. 40 billion suns in a single point, with an appetite that emptied the heart of a galaxy. And it's still there, still waiting, at the center of everything it consumed. Number 1, the mass of everything we can see. We've spent this whole journey climbing a star wide enough to bury Saturn's orbit, a galaxy 6 times the Milky Way, hiding in plain sight, a black hole heavier than galaxies, a wall of superclusters 1 billion light years long, each one bigger than the last, each one straining the limits of what a human mind can hold. So let's finish by asking the only question left. What if you added it all up? Every star, every galaxy, every cluster, every black hole, every cloud of gas in the entire observable universe. What's the total? Cosmologists have actually tried to answer this. And the number they land on, for all the ordinary matter in the observable universe, is somewhere around 1.5 times 10 to the 53 kilograms. That number is meaningless to us, and that's the point. There's no way to feel it. It's a 1 followed by 53 zeros, roughly. It contains every single thing we have talked about today. WOHG64, Muchepe, that entire billion light-year wall, the 40 billion solar mass black hole, all of it, every star in every one of the 2 trillion galaxies we think exist, is somewhere inside that one figure. And now, the two twists that should genuinely reorder something in your head. First, that colossal number, all the matter in the observable universe, is only about 5% of what's actually out there. Ordinary matter, everything that glows, everything made of atoms, everything we've ever seen or touched or been, is a rounding error. The other 95% is dark matter and dark energy, things we can barely describe. So even that unthinkable total is just the thin, bright skin on top of a universe made mostly of mystery. Second, and this is the one that stays with me, it's the mass of the observable universe, the part we can see. The observable universe isn't the whole universe. It's just the region close enough that light has had time to reach us since the Big Bang. Beyond that edge, the universe continues, and as far as anyone can tell, it may go on forever. There could be infinitely more out there, infinitely more stars, infinitely more galaxies, infinitely more of that unthinkable mass, past a horizon we can never cross, no matter how long we last or how far we travel. So here's where the journey ends. We started with a single dying star we finally managed to photograph. And we climbed and climbed past clusters and walls and monsters until we reached the total weight of everything we will ever be able to see. And even that, it turns out, is almost nothing. A bright fraction of a fraction, floating in a dark that has no known edge. We are very, very small. But look what we did. From inside all of it, blind to almost all of it, we still weighed the universe. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.